My presentation is on my top 5 tuning tips for MySQL. And so just a little bit before I get started, about myself, I've been a long-time DBA, over 25 years. Actually, I'm being kind. I started out with version 3 of Oracle. MySQL, I started with version 3.4, soon to quick upgrade to 4. Let me tell you, MySQL has come a long way since those days. I've been at SolarWinds for the last 11 years, and there I specialize in performance tuning. So I work with our customers, our prospective customers, looking at their databases, giving them some ideas of how to speed up. So there's the agenda today. This is only 25 minutes, and unfortunately, I found this out like last week. This presentation usually takes an hour. There's 60 or more slides, many case studies. I won't get to all that in this 25 minutes. I think I can keep it to 25 minutes, but I want you to know I've given them my whole slide deck, and that it's really something you should go through if you want more information. If you look and Google me at SolarWinds, I do have many different performance talks, and all of my PowerPoints are published there somewhere, so you can find them. But we're going to talk about my 5 tips. I'm going to talk a little bit about challenges of tuning, and then we're going to jump right in. And you can see them listed right here. In order to save time, we're just going to talk about them. I'm not going to walk through the agenda. Oh, sorry. OK, so challenges of tuning. How many people have ever tuned something and no one notices? Shame to say, but I have. And you know, a lot of times when you're tuning, how do you know you're working on the right SQL? How do you know you're working for the things that people are going to see? So a lot of challenges of tuning is just finding that one SQL statement that's causing all of your issues. Not only that, depending on your organization, they're siloed. You know, and there's people fighting over who should tune. Sometimes, how many people think developers should tune? Actually, how many people are developers here? Oh, OK. How many are DBAs? Just curious. Okay, how many think DBAs should tune? OK, I'm seeing some of this. And rightfully, a DBAs also have to keep the lights on, right? So, and they don't know the applications like the developers, but there's always that fight. So even that's a challenge before you even sit down and tune. So tuning is also never ending, especially as data grows, as workloads change, you know, as new releases go. You're always tuning. So it could be a good thing if you get good at it, but just realize it's challenging. Okay, so I'm going to go through my top 5 tips. Again, 25 minutes doesn't do this justice, and they're not the end-all, be-all to tuning. But hopefully there's something you can put in your tuning kit, you know, to think about when you hit that one SQL statement you're going to tune. So let's get started. My tip number 1 is monitor wait time. And the reason why I say monitor wait time, because that's the best way to find which SQLs to focus on. I mean, think about it. A database is usually 80% of the performance problems of most applications. If you can reduce the time spent in the database for your applications, you've given back time to your end users to actually affect the bottom line of your company. They're not sitting there waiting for a response. Years ago, I worked for a telecom company, over 5,000 service reps in the Western and Midwest, taking orders on the phone. If that order took 10 minutes and 9 minutes of that was waiting for a response from the database, I could speed that up. I could affect the bottom line. So by looking at wait time and how long a SQL statement works through the database, and not only that, by most of the databases, especially MySQL, is instrumented with wait events and thread states. So you can get real good ideas of what resource it's using up or waiting on. So if you were to look at every step that SQL request takes, time each step, and not only that, record off the resource that's used up and wait on, you could rank your SQLs on where to focus on to tune, and not only that, you have great clues on how to tune. And that's my biggest tip, because it's the fastest way to find the problems in your database, and it's the quickest ways to solve them. Now, you can do this in MySQL through Performance Schema. Performance Schema is a database that's in memory only, not persisted to disk, and it records information about all the processes as you know the SQL statements get executed in the database. It used to be in the earlier versions, the default was to turn off the performance schema. You took a performance hit if you ever access it. You took a performance hit if you even ran it. So after 5.6, they've actually rewritten it so it's much more, performs much better, less footprint, no overhead or very little overhead, so you can access this information. It gives you, and they've actually instrumented more stuff. So in the performance schema, you not only get current information about the processes and the SQL statements, but you can also get some history as well. You get it at a very detailed level. Picoseconds. It's the best instrumented database I know of that it's down to that level. It gives you information on statements, stages, and wait events. So now you know what resources are being used up by that SQL, and not only that, each one of those have clues on how to tune. So you've got a start. Performance schema beginning in 5.6 is now on by default. The storage engine, which really helped us a lot, is now defaults to NODB, which is more transactional. And not only that, in 5.7, they've actually added new tables. There's like 87 in 5.7, where there were 17 in 5.5. Reduced footprint and overhead, like I said, over 1,000 instruments. One thing, if you download 5.7.10 from Oracle, they actually give you a sys schema. Anybody old Oracle DBAs? Okay. If you like the $V tables and the X tables, what they've done is they've actually made views on the performance schema and summarized. So you don't have to look at picoseconds. You don't have to figure that stuff out. And it's summarized that data to make it much more easier to read. Okay. So here, if you want to do this methodology, it's real simple, not rocket science, guys. These are not all the tables in the performance schema and the information schema. They're the tables you'd want to visit, and not even all the columns, but they're the columns you'd want to put in your select statement to get this information out. We have and I've got some information from the information schema too. We've got the process list. Can you guys see that? I can zoom in if you can see it all. Okay, we've got the process list, we've got the NODB tables in the information schema. And they give you lots of information on transactions. But if you were, actually I think I will zoom in a little bit so I can get my pointer here. But if you join the process list into the thread tables, you can see that you can get user information, host, what database, what command, you can get all that good information. Not only that, you can take that and join it into events waits current and events statements, where you can get not only the object and the operation, but you can also get the rows affected, the rows sent, the number of executions. You get all this good information. And then not only that, if you go to the NODB tables, you actually get the transaction information. You can see locking and blocking, who's waiting and who's actually blocking. So very good, very granular information. This query, and I expect you to read it back there. No, I'm teasing. I don't expect you to go through it right now, but basically this query is all you need. Like I said, the performance schema is in memory only and not persisted, so you're going to have to poll this at some interval. Our product, DPA, actually pulls it every second. But it's very lightweight because it's all in memory. Not much data is really brought back. But you notice all those tables I'm referencing, and basically what I'm doing here is I'm just inserting it into a table of mine to persist it. And so I've got the results on the next query. And so I created a table called WTA data. And I thought, OK, I'm going to sit here and I'm going to poll that query every second. And I did this for 3 minutes with a load running. I usually use HammerDB, where I configure it with different SQL statements, and I run usually between 5 and 8 users, on a little VM. So I had a load that was pretty comparable. And so what you see here is I just go get the data that I collected. I order it by total time, and then I actually order it by wait operation and time in seconds. And so I got my queries coming back. Now what I want you to notice is my wait operation, time in seconds, and the total time. Now the bottom two are my queries that have spent the most time in the database. If that's all I had to tune, if this is all that was running in my database, I'm not going to look at the one that spent 2 seconds. on an insert, I'm going to look at the one that spent 24 minutes, mostly on a fetch. What is a fetch? Well, that's where you can go to the manuals, you can find great ways to tune that time. And so that's what I'm talking about, looking at and monitor wait time. Here's a graphical representation of wait time. And if you notice, this is really a view of about 10 queries. And I'm running this little DVD rental database that they give you. And so I've got overdue, a query that I named overdue, some selecting of films, and then I've got a weekly sales report. Those are my top three queries. The others didn't spend much time in the database. My very top one, overdue fees, spent 100% on sending data over 20 hours. That's where I know to focus. Sending data means it's doing a lot of disk access. Well, I got a clue on how to tune now. My third one down here is waiting for a metadata lock. I know where to go focus and tune that. 16 hours on that. So just real quick. Other benefits, like I said, it's documented very well. We document it with our tool, but you can actually go to the manuals. You'll see solutions on any of these wait events and thread states. My most favorite benefit, though, is basically you can gather baselines. When I tune, I like to first get my baselines. Reason why is I want to make sure I improve it when I'm done. I don't want to make it worse. So I like to get how long it takes now, and I usually grab the rows examined and the rows sent for comparisons. Because if I can reduce the rows examined with the same amount of rows sent, I know I've improved it. Because after all, what's the most slowest component on a computer? I/O, right? If you're going to reduce the amount of I/O you're doing, you're going to speed it up. Okay? So with wait time analysis, you can basically do that because we're collecting that rows examined, rows sent number of executions. Here's just an example of this one query that I made of. It's a sales quarterly contest. Very sluggish. 16 executions in 1 hour. 61 executions in 1 hour, sorry. Notice how much time with all the people running it spent. 18 hours and 21 minutes in that 1 hour. That was every active session trying to run that. They only did 61 execution total. Each execution took about 15, 16 minutes. Very sluggish. Quick way to find that is wait time analysis. Plus now I have my metrics that I can actually go look at and start tuning. Excuse me. Tip number 2, get the execution plan and really examine it, really review it. Now, MySQL gives you many ways to do that. You can do an explain just on the command prompt and give it the query, and it'll give you the explain plan. You can also do extended, you can actually format it. You can do a trace now in 563, which gives you even more information. It actually gives you all the permutations the optimizer thought about before it actually did the plan. And then MySQL workbooks. I have examples of all these. But what I want you to notice here, this is a complex little query, my little quarterly contest. I've got a lot of tables I'm joining. Here, I don't know how many, I didn't count them. But it gives you the type, it gives you the data access, which is very important because you can see this one type of all. What's that? Full table scan, right? It's reading all the data. No matter if I'm returning one row back or all the rows, it's going to read all the data regardless. If you look down, and I couldn't really get this all in one line, so you can see that that payment full table scan is actually reading over 300,000 rows. Very inefficient when all the other rows were 1 or 2. So something to think about when you're looking at an execution plan. There's a neat cheat sheet out there. It's old, but I like it because if you're not familiar with all the columns and everything in Explain Plan, you can actually download this. And it kind of explains all the columns and everything. I like it because of the extra fields, because extra field will show you temporary sorts, file sorts, temporary tables, I'm sorry, and then also any joins and any different conditions in the where clause. So it's kind of nice to have that as a little cheat sheet to see it. Here's just an example of explain extended. And this is kind of my favorite because I always do an explain extended because what happens if you do an explain extended and give it the query, and then after that you do a show warnings, it'll actually tell you what the optimizer transformed the query to. So what I always do is I always check that. I look for implicit conversions. I look for anything that might be out of the ordinary that is trying to substitute that I didn't give it, because the optimizer will try to fix it for you. So I always look at that very carefully because it might help you write better SQL. This is an explain using format equals Johnson. The only reason I like this is kind of like the format of it because it'll tell me all that information in one little space about each object. But the main thing I like is I like this used key parts because it tells me, yeah, it used my primary key, which was really 3 columns, but it only looked at the first column. So is that a waste? Should I make a better index? Or maybe I didn't give it enough information that it's not using the whole index. So those are the type of questions you want to ask when you're examining the execution plan. Here's optimizer trace. I think it was 563 it became available. This is interesting because it shows you all the permutations the optimizer thought about before it came up with the plan. And how you set it on is you set optimizer trace equals, in quotes, enabled equals on. And this is actually a case study I'm going to get to, but we give it the query. And then where it stores this information is in information schema. So you have to look at the table optimizer trace. Now the gotcha is default is only 16K. So it will error out if you have a query with lots of joins. So because it has to go through all the permutations to figure out the plan. So you can see an error message like this down here where it says missing bytes. I ran a room with just my 3-table join here. You set it off by either getting out of MySQL or you can do enable off to set it off. But the thing is, up here, you could actually configure it to either give it more memory, which I did. I gave it a meg just so it would give me the whole plan. Or you can actually do this thing, set optimizer trace features, greedy underscore search equals off. And that'll make it not as verbose, so it'll fit in there. But again, the thing I like about it is it'll tell me, right, all the costs that it considered. And so then you can look at the plan, the final plan, and see what it led with. In this case, you'll see I have 3 tables. I have student, which is 161. I have registration, cost is 225. And I have class, which is cost of 10. I know where I'd like it to lead with, but it doesn't. It leads with student. Question? Well, yeah, but yeah. Okay, so I want to go through this case study. And actually, it helps with the rest of my tips. So this case study actually came in via Oracle. So good segue. It was an Oracle case study. It was a university. And what their business issue with this query was they were trying to get their billing done. And they were asking the business question, who registered yesterday for classes? Now, I've changed it. I'm only looking for SQL tuning. But basically, it's the same thing. And they couldn't get it done. They actually called us because they couldn't figure out what was causing their billing cycles to slow down. Simple query. We looked at it, and it was really a simple query. They were selecting first name, last name, and registration sign-up date from student, joining into registration by student ID, and then they joined into class by class ID on registration to get the class that they wanted. So I've got where class name equals SQL tuning and sign-up date, the registration sign-up between a date, because it was always yesterday and a rolling yesterday. Now the thing is, the registration table was historical. It was quite large. It was a university. And so if a student ever dropped or canceled, they wouldn't delete the record. They'd just mark it as canceled. So we were looking for only active records. you can see here when I ran it, and I actually ported it from Oracle because I wanted to see if it would behave the same. And so I ported it over to Oracle, and it's actually ran a little better in MySQL. 5.5 seconds rather than the 20-some seconds I think it was running before. 13,000 executions. It spent 19 hours and 55 minutes in the 1 hour with all the processes running it, because of course I made a load out of it. Look at my rows examined. 1.2 billion. Look at the results that it returned. 173,000. You know, over 13,000 executions. I mean, a lot of excess reading, wouldn't you say? So anyway, so that's our case study. This is my final thing on the explain plan. I like Workbench. That's what I usually use because I like the graphical. And the thing about Workbench, if you don't use it, you might want to consider it because it'll actually highlight high steps. And you know, it gives you some recommendations as well. Plus, it has a nice GUI interface so you can type your SQLs and stuff. Thing about this, remember our costs? Class was 10. I wanted it to go to class. No, I went to student. I did a full table scan on student, 87, well, 8K, so 8,000 and some records. Then it dipped into registration with nested loops, 4 rows, and then finally it dipped into class and got 1 row and reported that back. So what do you do with an execution plan? When you look at it, you look for the expensive steps. Well, we saw that. It's student, right? So what do? I look at the cost. I look at rows examined versus rows sent. And I also look for full table scans, any index scans that are reading lots of data. I review the predicate information. I look at my indexes, because what I want to do is I want to make sure if I've got an index, I want to make sure that's the right index. It warrants that it's being used. And I want to make sure I didn't turn it off somehow. I didn't put a function around it. I didn't, you know, give implicit data conversions so it's doing something silly. So I want to make sure it's using that index. And then it's always good to avoid temporary and file sort activities. And you'll see this in the extra column. This is just a quick example of what that looks like. You know, I'm just doing a group by. I'm just counting my number of students. I order by and group by, and sure, it's going to make a temp table, and it's going to throw it into file sort. So if you can avoid that, that'll help as well. Tip number 3, gather the object information. Okay, I found students being large. So now what I want to know is everything about student. What's his size? Where does it live? You know, what's its column makeup? Any indexes? All of that's good stuff. So you can see here, you can do a MySQL show -- and you can put either the database and get the whole database, or you can do a database table, or you can get as specific as putting the whole database table column. But I just did database here, and you can see my class has 1,000 records, registration has 80,000 records, and student has 9,000. I said 8K, but it's 9,000 then. So as you can see, it gives you data length and index length and all that. It's also important to check, especially the columns you're referencing in the where clause. What's their cardinality? Is it very selective, or is it maybe 2 values and 90,000 records each? Also know if there's data skew or not, because the optimizer will look at all that, and it'll make it either ignores it in most cases, and that's why it's behaving the way it is, or you have to do other things to get it to run properly. And also look at your selected columns. I hope you don't select star. How many have code like that? Okay, well, anyway, I won't go there, but that's one of my pet peeves. Okay, review the indexes, as I've said. Make sure those indexes can be used. If it's multi-column index, make sure your where clause has the left leading column. Otherwise, it won't use it. It'll ignore the index entirely. Step number 4, find the driving table. And what I mean by this is I want to read the least amount of data first with that query, and then fill in the select part of the query. I don't want to read all the data and all the tables and throw them all out at the end. That's just wasted work. So if I can find the most selective table, and I can drive with that, then I've already done my tuning. So how we do that and how you can arrive at that, I have a technique that I like to use. This is an oldie but goodie book, SQL tuning, but it still works today and works in every database type and actually covers most database types. So if you want to know more about SQL diagramming, it's just a technique to filter and find where the driving table is and come up with the best execution plan. And how you do that is you draw an upside down table, or upside down tree, it looks like, with your detailed table first, and arrows out to any of the master table or lookup tables. So in our scenario, we had a registration table, a lookup into student, a lookup into class. The numbers here, and let me just show you that real quick, on the arrows are basically your join estimates. So what we're saying here is for every one student, I have about 5 registration records. And for every one class, I have about 30 students. Maybe small for a university, but you get the idea. And you can actually, it's a simple query to get those. But what I'm saying here, for you joining these tables, to get any one student or any one class, I should never have to read more than 150 rows. If you're reading more than 150 rows and doing this query, then you've done something wrong. You either don't have an index on your join columns, which is usually the case. The next thing you look at is your filtering predicates. So I had 2 filters. I had one on registration, where sign up date equals yesterday, if you will, and a canceled flag equals in. And then I had another one on SQL tuning, where class name equals SQL tuning, sorry. So 2.2% of class would be read with that filter, as opposed to over 5% of registration. Which is a better filter? Class, right? Only 0.2. Only 2 records are going to be read from class. So how do I want to drive it? I want to drive it by class. Least amount of data first, and then build upon it. So let's go put an index on class name. And did this. And here we go. So as you can see here, our execution plan suddenly changed. No longer doing student, I'm driving by class. I'm reading 2 rows, do nested loops into registration, and then I do a nested loop into student with 1 row. So right now, looking at this, I know I've sped it up. Did we improve it? Yes, we did. So here is my testing using wait time again. And you can see up to 30 seconds on some average executions here. When I finally tuned it, instead of 5.5 seconds, I got it down to 0.72 seconds, 0.072. And look at my throughput. Hardly any executions were happening. Hardly any rows were being affected or sent. Look at my rows examined at the beginning, though. 1.5 billion, and I got it down so you can't hardly even read it. Well, 12 million, okay? Anyway, so I improved it. This is a report, or this is something you want to report to management. Look what I did. might cost you, save you some, might get you a raise, I don't know. But you always have to ask yourself, are you using the best index? And there's many indexes here, and I'm running out of time. I got 10 minutes, and I know you guys can read my slides. And like I said, I have all the slides, even more case studies on this in my deck if you download it. But there's lots of other types of indexes to consider with MySQL. You've got covering indexes, you've got partial indexes, you've got virtual columns that you put an index on where it doesn't even keep the data in the table, it just updates the index. You've got all these neat things. There's a list of indexes you can look through. But just realize there's some more that you have to do if you really want to eke every little bit of performance. But don't drive yourself crazy. You can get burned out on tuning too. If you have to kind of know when to stop. But here I thought, well, I'm going to add a covering index. Try it. Covering index says, add all the columns in your query in an index so it doesn't have to make that extra lookup in the table. So I added and made a covering index. Tip number 5. Injure in the air, out the stupid. This is my favorite tip. This is probably where most of my problems happen. Is, avoid cursor or row by row processing in any relational database because they like set processing. Don't do parallel queries in an OLTP environment if you can avoid it. Tune the query. Don't get lazy. Alex actually has a nice blog about parallel. Hard-coded hints. Try not to do that. Hints get put in there and forgotten, and then it's a whole release to put new code into production. Nested views, subqueries. Try not to make it complex. Optimizer can only think through so much. It's still a machine. But getting better. Abusive wildcards, no where clauses. How many people use code generators? Okay, there's a few, but just be careful. They do awful code, awful SQL anyway. Implicit data conversion, I can't tell you enough. Turns off indexes. Even if it doesn't turn off an index, it's taken CPU cycles to do that behind the scenes when it doesn't have to. And then finally, make sure you can use indexes. If you get things in the where clause, make sure you have an index on it so you can search on them appropriately. My stupid thing in this case study, remember I said I ported it from Oracle? I ported a date from Oracle. A date is really a timestamp in Oracle. Has the full thing. I didn't have to do a between because this is a date. The date, one date. I was looking for yesterday. I could make it equal to yesterday. I didn't have to do a between. Covering indexes don't work on ranges. So my putting a covering index did nothing at that point. It actually added more records it had to read. So at this point, I said, OK, instead of doing a between, just equal it. So that's what I did. And let's do, go down. And so here, you can see now it's using the covering index, doing 2 rows instead of the 40 rows. It's doing only one row. I improved it greatly. So I'm done. And so there is again another chart of doing that. So in summary, quick 5 tips. Just look through them, work through them, think about them each time you run into a query, and make sure you're working on the right query. That's it. Any questions? Thank you.